Section 7.3 covers acetic and basic anhydrides. So the first one we're going to talk about are acids. When we produce an acid and we call it an acetic anhydride, anhydride just means without water in the product, but there is water on the reactant side right there. So what you're going to see is you're going to see a formula that has a non-metal oxide plus water, and it's going to make an acid, specifically what we call an acetic anhydride. So an example of this would be right here. This is sulfur trioxide. Notice how this is a non-metal oxide plus water. It's following this formula and it makes sulfuric acid. So how you figure out the product. So questions are going to ask you to figure out the product. This is not very scientific. All we're doing is smashing the hydrogen and the oxygen in between the other nonmetal. So for example, on this one, notice how you have two hydrogens. The hydrogens are always going to be written first because it's an acid. And then you have the other nonmetal that's not oxygen, which is the sulfur. Notice how you just have one of them. And then you're going to add up how many oxygens you have. We have 3 and 1, so we're going to get an O4. And then this should make sense because if you break it apart again, it should break up into a hydrogen, and because we're dealing with oxygen, it should have a polyatomic ion in there. So right here, hydrogen's a plus, SO4 is sulfate 2 negative. If we swap and drop, that's where we get the H2SO4. Let's do another example. This one right here is carbon dioxide. Again, a non-metal oxide plus water. So here we're just going to smush it together. Hydrogens go first. We have H2 right here. Then we'll do our other substance that's not oxygen. So that would be the carbon. Notice how you just have one of them. And then we're going to add up how many oxygens we have. We've got 2 and 1. So we get an O3. So our answer here is H2CO3. This is called carbonic acid, and this is the acid that is carbonation. So it just produces that carbon, the carbonation in your fizzy drinks. Okay, the second type of anhydride we're going to talk about is a basic anhydride. So a basic anhydride, very similar formula. You're going to have, instead of a non-metal oxide, you're going to have a metal oxide. So any kind of metal and oxygen plus water, and then you're going to get a basic anhydride, which is the same thing as a metal hydroxide. And notice no water in the product. Okay, this one is more scientific because we're going to look at charges. So right here, we've got a metal and an oxygen. So we have a metal oxide plus water. So for our products, all we're going to do is take the metal, look at the charge. So in this case, sodium has a +1 charge, and then a hydroxide, which has an OH negative. So remember, hydroxide is an OH negative. And you're just going to make sure the charges cancel. If they don't, you're going to swap and drop. So +1, -1, that's going to cancel. We're just left with sodium hydroxide. And then you can always balance it. If it asks you to balance it, balance it. If it doesn't, you don't need to. Okay, let's do this other example down on the bottom. On this one, we have magnesium oxide. So again, here's our metal and our oxygen plus water. So on the product side, because we have a metal oxide, we're going to do magnesium. It has a 2 positive charge because it's in group 2. We're going to bond it to the hydroxide, which has a -1 charge. These charges don't cancel, so we're going to have to swap and drop, and when we do that, the OH goes into parentheses and the 2 comes down. So on this one, we get magnesium hydroxide as our answer. Okay, let's choose another metal. Let's say that we're doing aluminum. So aluminum oxide, if we swap and drop our charges, we get Al2O3 plus water. Let's say that we have to predict this product. So you're going to have aluminum. Aluminum has a +3 charge. Hydroxide has a -1 charge. Those charges do not cancel, so we're going to swap and drop and put the OH in parentheses with the 3 on the outside. Okay, so you're going to get problems where they're going to make you figure out the product. They might give you a word equation, and you might have to say, oh, this is a metal, And this is an oxygen, so therefore I'm going to get a metal oxide if it's bonded with water. So just watch out for those types of reactions. Okay, next section is 7.4. And 7.4 is just about strong versus weak acids and bases. These have to be done in a lab setting. So on pages 195 and 196, there's a list of strong acids and bases. I would just make sure that you know the 3 strong acids that it lists. So let me hurry and write those down. There's sulfuric acid, which is H2SO4. So make sure you recognize the name and the formula. Another strong acid is called nitric acid. This one is hydrogen and nitrate bonded, HNO3. And the last one you're really familiar with, this is hydrochloric acid, and this one is just H with a Cl. So I would just know the 3 strong acids, and again these are on page 195, and then there is a list of strong bases on 196. Okay, let's talk about what makes an acid or a base strong or weak. So if we have a strong acid or base, it completely ionizes. So remember that word ionize. It means that it's going to break apart into ions. So completely means 100% broken apart. So for example, we know that hydrochloric acid is a strong acid. So if we were to look at this on a very small scale, it would be hydrogen ions and chloride ions. You would not have a molecule of HCl together. You would just have hydrogen ions and chloride ions. And the reason why this is strong is because you're getting all of these hydrogen ions are separating from the molecule. That's why it's such a strong acid. Same viewpoint for a base. Sodium hydroxide is a strong base. The sodium hydroxide, it would completely ionize. You'd have sodium ions. And then you would have your hydroxide ions. Again, completely ionized, which just means they're breaking up into their ions. Okay. All right. If we're dealing with a weak acid or a weak base, then it's mostly insoluble, which means that it doesn't dissolve. Or doesn't, maybe that's not the best word, it doesn't break apart into ions. That's a better way to put that. Okay, and notice how it says it about 1% disassociates. The only difference between the word disassociate is dealing with a polar compound, and just kidding. Disassociate, this is always so weird, deals with an ionic compound. Sorry about that. And ionize deals with a polar compound. Both of them mean the same thing. It just means that you're breaking your substance into ions. It always tricks me because I would think ionize would be go with an ionic bond, but it goes with a polar compound, which means that you're dealing with 2 nonmetals, but one of them has a more positive charge than the other one, like hydrochloric acid. And then dissociation means ionic bond breaking apart. Okay, so if it's insoluble, it's not going to break into ions. So for example, HF, hydrofluoric acid, is a weak acid, so it would mostly stay in its molecular formula. And only about 1% would break up into a hydrogen ion and a fluoride ion. And the same thing would happen with a base, is that it would mostly stay in its molecular formula. So an example of a weak base would be strontium hydroxide, for example. So if we were to draw a structure of strontium hydroxide is SrOH with a 2. Most of them would just stay in its molecular formula. So you'd have a whole bunch of strontium hydroxide. You get the gist here. And then only about 1% will break apart into its ions. Right there. Okay, so that covers 7.4. If you have any questions, let me know, and have a great day. Bye.